Voyager 3. Our team lead is Eliot, Khachi, and our team members are Caroline Castro, Andrea Coronado, Mohamed, Amin, Mannai, and Solomon Than. The outline of the project entails mission information and analysis, mission goals, concept and summary, assumptions, theories, and key constants used, calculations used to meet mission requirements, tools used and assumptions used, any optimizations used, our approach to mission objectives, and additional graphs, calculations, and animations. The Voyager 1 and Voyager 2 were spacecrafts used to explore the ARO solar system to gather data about outer planets and are both currently drifting through interstellar space after completion of their mission. These craft explore all the giant outer planets of the solar system and 48 of their moons. Furthermore, they both utilize solar gravitational lensing, which uses the light that bends around the sun's gravitational field as a telescope. Voyager 3 will explore the ISM with new instruments and technology in an effort to directly image an exoplanet using SGL. The mission overview. The Voyager mission is expected to go from Earth departure to an observable point at 550 AU. The launch window is between 2035 and 2050 and is set to reach ISM as quickly as possible. The vehicle will remain observable until it reaches past 550 AU. Flyby maneuvers are used to reduce the fuel mass. The total delta V of the mission is 31.6 kilometers per second. The launch energy of the launch is 80.9 kilometers squared per second squared, and the time of flight to reach target is 15,611 days. The mission is projected to launch from Earth on December 25th, 2043, and fly through space on May 22nd, 2048, when the craft will do a flyby of Jupiter, which will project the craft to reach 550 AU by September 20th, 2086. Modeling assumptions. The Wolf 1061 system is assumed to have a rate ascension of 16 hours, 30 minutes, 18.1 seconds, declination of negative 12 degrees, 39, and 45.325, and a dry mass of 100 kilograms. The Space Launch System, or SLS, being used along with the Nuclear Electric Xenon Ion System, or Nexus engine. Flybys performed are assumed to be only a few kilometers above the planet instead of around 50 kilometers. Lambert's theory was also used during calculations, as well as a modified version of the patch-conic approximation method, which assumes non-circular orbit rather than circular orbit because NASA's data was used rather than the hand calculations. And any sphere of influence is assumed to be zero once the craft leaves the sphere of influence, and infinite while in the sphere of influence. Some more assumptions are that Earth's radius is 6,378.1 kilometers and the atmospheric altitude of Earth is 100 kilometers. It's also assumed that Venus's radius is 6,051.8 kilometers and the atmospheric altitude of Venus is 120 kilometers. Of Jupiter, the radius is 71,492 kilometers and the atmospheric altitude is 69,911 kilometers. The launch energy is 75.758 kilometers squared per second squared, and the V infinity is 8.7 kilometers per second. Techno calculations analysis. Originally, we attempted to use Malto, but we're having issues running the program through our devices, so we stuck with MATLAB and FreeFlyer for our calculations. Every simplification made was in order to get more accurate numbers and reach our mission goal. So, starting with our first attempt, we tried Earth to Venus to Earth to Jupiter to 550 AU. Launch flyby and arrival date were calculated with MATLAB code, but delta V wasn't obtained from FreeFlyer. The second attempt was Earth to Jupiter to Uranus to 550 AU. No dates for launch, flybys, or arrival, seeing as the code took too long to run, it did not produce good numbers. Our third attempt was Earth to Jupiter to 550 AU. Originally had trouble with generating delta V's to calculate launch mass. And then on our fourth attempt was Earth to 550 AU. It was a straightforward flight path and it gave positive results, but it was too simple to actually use. So on our fifth attempt was Earth to Jupiter to 550 AU, which solved our original bugs and problems, and we were able to produce good values. The following formulas were used to calculate S, S max, delta V, V infinity, and C3, which stand for the maximum, S, possible and current S, the final velocity after a flyby, the hyperbolic velocity at infinity, and the launch energy respectively. The hyperbolic velocity at infinity is found by subtracting the velocity from the parabolic velocity. Our final design, we chose the exoplanet system Wolf 1061 due to its close proximity to Earth. The TRAPPIST-1 system was also considered due to its lower inclination. However, the velocity expended to travel such a distance outweighed the velocity lost by an inclination change. The launch vehicle selected is the SLS due to its high thrust and efficiency, and the Earth to Jupiter to 550 AU was the only viable option since it was relatively fuel efficient and was verifiably possible through MATLAB and FreeFlyer. The following is the pork chop plot for the initial design. This shows the pork chop plot we used versus a pork chop plot that was generalized by the optimization tool. As you can see, they are very similar. Here is the pork chop plot for a final design. The pork chop plot we use versus a pork chop plot generated using the optimization tool. See, there is slight change, but still a same general pattern. And our summary. Earth to Jupiter to 550 AU was the best trajectory found that allows us to successfully meet our mission requirements. We were able to fly by Jupiter, allowing us to save fuel along the way. Trajectory optimization tool ARO by Adam Hardin should have been used to help us with our pork chop plots and dates. More time should have been put into Multiple FreeFlyer to generate trajectory from dates provided by the optimization tool instead of putting so much time into our MATLAB code for our dates. The following are our trade studies which help us decide on which exoplanet system or which launch vehicle to use. Additionally are our backup slides and our references.